6.8, derivative of the exponential function. The last time we discussed that there is correspondence between power function and logarithms. Correspondence is that one is the inverse function of another. And so if y is equal to a to the power x, then logarithm with base a of y is equal to x. And this is our correspondence. And using this correspondence, since we know the derivative of the log, we can find the derivative of exponential function. That is our plan. So suppose we have function, but let it write in this way, y is equal to a to the power u, where u is some function of x, and we want to find dy over dx. So using that correspondence, y equals a to the power u is the same as u equals logarithm of y with base a. And let's differentiate this equation, because we know how to differentiate the logarithms. Again, a shouldn't be 1 and should be positive. Otherwise, neither exponential function is not interesting and logarithm is not defined. And so what we get? We get that du over dx is equal to 1 over y times logarithm with base a of e using our rule times derivative of y with respect to x. But our goal is to express this one. So what we get? We get that dy over dx is equal to 1 over logarithm of e with base a times y times du over dx. But what is our y? We started that y is equal to a to power u, so we get that d over dx of a to the power u, which is function of x, is equal to 1 over logarithm of e with base a, and instead of y I can write a to the power u of x times du over dx. And that's what we needed. We can simplify it further. 1 over logarithm of a, or logarithm of e with base a, is equal to logarithm of a. We discussed it last time. Let's do it again. Recall that there is change of base formula. Logarithm of b with base a is equal to logarithm with some number c of b divided by logarithm of a with base c. For any ABC, that such that all these logarithms exist. And so let's apply this formula with a equals a, b equals e, and c equals e as well. Then we get that logarithm with base a of e will be logarithm with base c, which is e, of e divided by logarithm with base e of a. But logarithm is base e of e is just 1, while on the bottom we got just the definition of the natural logarithm of a. And so we get that logarithm of e with base a is 1 over logarithm of a, natural logarithm of a, and thus 1 over logarithm of e with base a is equal to logarithm of a. And coming back to the formula that we derived, we see that we can write it in the following way. D over dx of a to some power u of x is equal to a to the same power times logarithm of a times derivative of that function. And in special case, when a is equal to e, what we get? We get that d over dx of exponential of u of x is equal to exponential of u of x times logarithm of e times d over dx, but again, natural logarithm of e is just 1, and we get that d over dx of exponential of u is equal to the same exponential times derivative of the exponent. If u of x is just x, then we get that d over dx of exponential of x is equal to just exponential of x, because derivative of x gives us just 1. And so this function, exponential of x, has a very nice property. If you differentiate it, that the derivative will be the same function. Okay, let's do some examples. Y equals 2 to the power x squared. So it has the form a to power u of x, where u of x is x squared. And so we can use our first rule. And so what we'll get? We'll get that derivative of y, which is derivative of this function to the power x squared, is equal to, so first of all, it's the same function times logarithm of 2, because a is equal to 2, and times the derivative of the exponent, so derivative of x squared. And so derivative of y is equal to 2 to the power x squared times logarithm of 2 times 2x. Another example, when you have y equals exponential of sine squared of x. What is y prime? The same strategy, but in this case, we have e as a base. And so we don't need that logarithm of a, and y prime thus will be initial function times the derivative of the exponent. And so that gives me derivative of sine squared using the chain rule or generalized power rule. That gives me 2 sine of x, and then derivative of sine itself, that gives me cosine of x times exponential of sine squared of x. And of course, you can use trigonometric formula that 2 sine of x times cosine of x gives you sine of 2x. So slightly becomes more compact. What about the next example, when we have y is equal to logarithm of tangent of exponential 3x. Okay, see, very complicated function, but if you do it by steps, it is not that complicated. So first of all, we see that it's natural logarithm. So the formula is easier for this one. So I get, first of all, I have y is logarithm of some function u of x, natural logarithm, and derivative thus will be 1 over u of x, which is tangent of that exponential, times derivative of that u. So tangent of exponential of 3x prime. So that was first step. On the next step, I need to differentiate tangent. And that gives me secant squared of that exponential 3x. But since it's a composition of two functions, I need to differentiate that exponential as well. And the third step, the last step, is the following. So you get secant squared of that exponential divided by tangent of that exponential and times derivative of that exponential, which is exponential itself, times derivative of 3x, which is, of course, gives me 3. And so I get that y prime is equal to 3 times secant squared exponential of 3x times exponential of 3x divided by tangent of that exponential. Of course, you can simplify it further using the definition of secant and tangent, but this is fine. The next example is more general, and it's quite tricky. So y is equal to x to the power tangent of x. So first of all, we see that the base of our exponential function, so usually we have a to some power u of x, where a was some constant, right? But here we see that x is not a constant, of course, so our base is also changing. But what we can do, we can play with our function, so it will take the form that we know how to differentiate. So what do I mean? Let's consider natural logarithm of both sides. So logarithm of y will be logarithm of x to the power tangent of x, right? But then, using the property of the log, I get that logarithm of y is equal to tangent of x times logarithm of x. The third property of the logarithmic functions. And now, there is no such thing as some function to the power of another function. It's just the product of two functions. And it's, of course, easy to differentiate. Now, on the left-hand side, we have derivative of the logarithm, where y is also a function of x. So we need to be careful. And derivative of tangent times logarithm of x. So derivative of logarithm of y using our rule is 1 over y of x times derivative of y. And it's equal to, first of all, I need to use the product rule. And that gives me, say, let's differentiate first logarithm. So it's tangent of x times derivative of the log, which is 1 over x, plus derivative of the tangent, which is secant squared of x, and times logarithm of x. But our goal was to find derivative of y, and thus dy over dx is equal to y times tangent of x divided by x plus secant squared of x times logarithm of x. But our y was x to the power tangent of x. So we get that dy over dx is equal to x to the power tangent of x times this expression. So the remark is the following, that you cannot use that rule that we discussed, d over dx of a to the power u of x, which is 1 over u of x times logarithm of a times derivative of u, in this case, because a is not a constant in this example. So a is equal to x. If we try to do that naively, so what we'll get? We'll get that d over dx of x to the power tangent of x. We'll get 1 over tangent of x. Oh, sorry. I differentiate the logarithm. It's a to the power u of x times logarithm of a. So what we get? We'll get the same x tangent of x, so that part coincides, but then we'll get logarithm of x times derivative of tangent, and that will be x to the power tangent of x times logarithm of x times secant squared of x, right? So again, this part is the same as in the right answer, but this part represents only half of the stuff in the parentheses. So there is no this tangent of x over x in this formula. So that's why you cannot use it. First remark. And second remark, that it can be generalized to the function that has the following form: f of x to the power g of x. So if you want to differentiate such function, again, there is no rule, but what you can do, you can consider logarithm of y, and that will be g of x times logarithm of f of x. And then differentiate both sides and do the same steps that we did in the previous example. Maybe third remark, so other way to think about it. So suppose you have sine of x to the power 3x squared, something like this. You can consider the logarithm of y, that will give you 3x squared times logarithm of sine of x, and then differentiate. So this is our way that we used before, but also you can say that y is equal to, and using the property that exponential function and logarithmic function are inverse to each other, so I can write that it is exponential of the logarithm of the function, because exponential of logarithm of any function is just function itself. Of course, if it is positive. But then what you will get? You will get that this is equal to exponential, and again you use the property of the log. That power you can put power in front of the logarithm. Logarithm of sine of x. And again, you see that it, in some sense, factorized. So now you have just the product of function and another function. So now it has form exponential of some function that we know how to differentiate. And this is another way how you can think about this problem. And so y prime will be exponential of u of x times u prime of x, and so on. Okay, and the last thing in this section that I wanted to mention is that some combination of exponential functions occur so often that they have been given some special names, and they are called hyperbolic functions. And let's discuss them. So what is the definition of hyperbolic sine? Sine, So you write sine, add extra letter h of x is equal to 1/2 exponential of x minus exponential of minus x. So this is called hyperbolic sine of x. And similar, there is hyperbolic cosine. So it's you write cosine and add extra letter h. And this is 1/2, but now you have sum of them. Exponential of x plus exponential of minus x. And this is called hyperbolic cosine of x. What are the properties? Let's briefly discuss it. Recall that we had sine squared of x plus cosine squared of x is equal to 1. And in some sense, you want some similar formula, but unfortunately, it is not straightforward. It's not sine, hyperbolic sine squared of x plus hyperbolic cosine of x squared will not give you 1. But if you consider hyperbolic cosine squared of x minus hyperbolic sine squared of x will give you 1. So you see, now you have minus. Still, you have kind of trigonometric identity, but it's hyperbolic trigonometric identity where you have minus instead. So let's prove it very quickly. You have that hyperbolic cosine squared of x is equal to, so it's 1/2 squared times exponential of x plus exponential of minus x squared. And this is what? 1/4 exponential of x squared. And that gives me, okay, let me write it like that. Firstly, plus 2 exponential of x exponential of minus x plus exponential of minus x squared. But using the property of the exponential function, that is equal to exponential of 2x plus 2. And here I have exponential of the sum. So this is exponential of x minus x. This is exponential of 2x. And this is exponential of minus 2x. So I get just exponential of 0, which is 1, plus exponential of minus 2x. So it is 1/4 exponential of 2x plus exponential of minus 2x plus 2. If you do the same with hyperbolic sine squared of x, you will get 1/4 exponential of x minus exponential of minus x squared. And you can check that it will give you 1/4, but in this case, it will be exponential of 2x plus exponential of minus 2x, but minus 2. And thus, hyperbolic cosine squared of x plus hyperbolic sine squared of x will give you 1/4. It's a common factor. And first, let me rewrite hyperbolic cosine plus 2 and minus hyperbolic sine. That gives you this. And then, of course, you see some cancellation. So exponential of 2x, exponential of 2x, minus 2x, minus 2x. And what is left? It's 1/4. And you have 2 minus minus 2, so it's plus 2. And that gives you 1. Sorry, I should start with minus here. Okay, and this is one important property. And also you have another important property that if you consider derivative of trigonometric hyperbolic, cosine of x, which is 1/2 derivative of exponential of x plus exponential of minus x, derivative, and that will be what? 1/2 derivative of exponential of x. Just exponential of x is what we discussed, while derivative of exponential of minus x gives me the same exponential of minus x times derivative of minus x, which is minus 1. And so it's 1/2 exponential of x minus exponential of minus x, and we see that it is hyperbolic sine of x. So hyperbolic derivative of hyperbolic cosine is equal to hyperbolic sine of x. And in the same way, derivative of the hyperbolic cosine or sine of x, which is 1/2 exponential of x, minus exponential of minus x, and by the same idea, you get that it is exponential of x plus exponential of minus x, and so it's cosine hyperbolic of x. So again, you see that there are some differences. So we get that derivative of hyperbolic sine is equal to cosine hyperbolic of x. So compare to the rules that we discussed in the trigonometric case, that derivative of cosine was minus sine of x, while derivative of sine was also cosine. So you see, they're almost the same, except that some signs are different. So sometimes you have extra minus, or sometimes you don't have. And what are the graphs of these two functions? Graph of hyperbolic sine of x looks like this. At 0, it has 0, because exponential of 0 minus exponential of 0 gives you 0. While at point 1, it is close to 1, but not exactly. And at point minus 1, it's close to minus 1. But it's approximately, it's not exact value. But what we can see from the graph and also from the definition of the hyperbolic sine, if we change x to minus x, we will change the sign of the whole function. So what I am saying that hyperbolic sine of x is an odd function. That means that hyperbolic sine of minus x is equal to minus hyperbolic sine of x, which is similar to the property of regular sine. While hyperbolic cosine of x, the graph of this function looks like that. Point 0, it is 1. At point 1, it's somewhere not very far from 1, but not exactly. And from the graph or from the definition, you can see that if you change x to minus x, your function will be the same. So that means that hyperbolic cosine of x is even function. That means that hyperbolic cosine of x of minus x is the same as hyperbolic cosine of x, which is also similar to the usual cosine. But of course, you see the difference between trigonometric functions and hyperbolic functions, because first of all, we know that trigonometric functions are periodic and are bounded. So they run from -1 to 1, while here both functions are not periodic, and also sine of x goes to minus infinity when x goes to minus infinity, and goes to plus infinity when x goes to plus infinity. While cosine of hyperbolic cosine of x runs to infinity on the both sides when x goes to minus and plus infinity. So they are unbounded. That is the main difference with comparing to the trigonometric functions.